Good morning, everyone. I hope you guys are having a great talk, great conference. So I would like to start by thanking my family for all the support I have. I wouldn't be here without them. So my talk is titled Perfidious, Make PE Backdooring Great Again. Perfidious is the name of library I developed while I was at Cybrary, interning at Cybrary. And Make PE Backdooring Great Again is basically a technique that I found while working and researching there. So I'll be discussing that technique, but I would like you to make sure that you keep an eye out for the bigger picture, which is the library itself. All right. So a little bit about me. My name is Shreyans Doshi. I'm a cybersecurity graduate student at University of Maryland. I also work as a teaching assistant there. And I have previously worked as a malware research intern at Cybrary. Those are my Twitter handles and my GitHub handle. So I'll start by giving some context about how this project got started. So when I first started at Cybrary, the initial project idea that my mentors presented me with was developing a machine learning model that could ingest large amounts of malware source code and basically create a malware sample that could evade the current endpoint detection techniques. Now, I had two questions regarding that project. First, whether it was legal for me to work on the project. Because I'm an international student in the United States, so I didn't want to get arrested. The second question was, even if I was able to develop all the parsers needed for all the various languages in which these malware source code is being written in, how would we find the quantity of source code needed to train a machine learning model? And as fate would have it, the mentor that I had for the project basically moved on to another company, and the project was left with me to do whatever I wanted to do with. So I had two options. I could idle away my 3 months at Cybrary, or I could basically figure out a way to work a reasonable amount of project that could be taken forward. So what I figured was, we don't have malware source code, but what we do have is a large amount of malicious PE files, right? So I had to find a way in which these PE files could be broken up into inputs that could be fed into a machine learning model. So in order to do that, the first step was to develop or find basically a parsing library that could split these PE files into small chunks of blocks that could be used as inputs to machine learning models. And although the PE file package that is available in Python developed by Arrow is a really great package, it is not meant to do those kind of things. It is meant to parse PE files and present that information as is. It is not really developed in a way that all those various fields inside the complex PE file can be edited, right? So what I decided was to develop Perfidious, which is soon to be released, a Python package that can be used to parse, edit, and assemble PE files from ground up. Basically, it creates an environment in which PE files could be split into individual Lego blocks, and they can be like used as and when you require. Basically, you could add and switch sections and stuff like that, right? So before we switch into PE backdooring techniques, it would be a good idea to have a refresher on what a PE file format looks like, right? So this is an overview of what a PE file looks like. It has a DOS header. It has a DOS stub, which contains this program cannot be run in DOS mode message or a complete DOS program. It has or may not have a rich header, which was until 2017 an undisclosed Windows header. It has the PE signature. It has the NT header, which is composed of the file header and the optional header. The optional header also contains the data directories table, which points to all the various data directories. And then it has the section header, which points to all the sections that are actually contained in the PE file, right? So this is what a DOS header looks like. It contains a lot of different fields, but the important ones are highlighted in yellow. eMagic is the MZ signature that we see at the beginning of a PE file. This helps the Windows loader know that, okay, this is a PE file, right? The next is the csum field, which is the checksum. So the checksum basically gives you the checksum of the file. There are several different checksums present inside a PE file. So whenever you alter a PE file, it's not just sufficient to change one checksum. You need to change each and every checksum accordingly. So checksum basically helps you to know whether a PE file has been altered in some way or not. The ELF ANU is basically the pointer to the extended PE header. This basically marks the starting of the optional header. So the next The next component that we have is the DOS stub. Now the DOS stub can either contain the DOS message, which can be a variable length string terminated by a $sign, or it can have a complete DOS program embedded within it. As if some of you have solved Flare challenges, you know there was a challenge which contained a DOS program, and the message in the DOS header was, this program cannot not be run in DOS mode. So basically you had to run that challenge in DOS mode. So the next field that we have is the rich header. Now rich header is a really interesting header, because this was historically used by Windows to nail a couple of really prominent malware authors, because rich header contains information about the compiler version and the compiler IDs that are used in order to compile that particular software, right? So this can be used in to create a sort of a signature that a particular malware author can have, right? So if you before this header was discovered, it was pretty much impossible for anyone to know that this existed, right? So this could be used as a signature to detect them. The next is the PE signature, which is PE followed by 2 nulls. This basically marks the starting of the NT header. So NT header itself is composed of file header and the optional header, and the optional header points to the data directories table. Now, file header is a really important header because it provides you the information about the entire PE file. It's the metadata about the PE file. So it specifies what type of machine this file can be run on, the number of sections that are contained in this particular PE file, the time date stamp, which specifies when this particular PE file was compiled, the pointer to the symbol table, number of symbols present in that particular symbol table, the size of the optional header that is followed by the file header, the characteristics of the PE file, which specifies what kind of guard CF table or what kind of basically security provisions are enabled on this PE file. The next section that we have is optional header. It contains a lot of fields, but the most important ones are the address of the entry point, which specifies at what address, at what offset inside the PE file the actual code execution begins. So this is where the code execution begins in the text section. The image base specifies what virtual address inside the memory would this particular PE file be loaded from. The base of the code gives you the basically base of the text section, so the offset to the text section. Base of the data gives you the offset to the data section, the first data section. So once the optional header also contains data directories table, it contains a list of data directories. The data directories format is basically the RVA to the data directory followed by the size of the data directory. It's basically a 4 byte by 4 byte list, right? So what happens is this enables you to actually find these data directories inside the PE file. Now, data directories basically contain metadata about various things. So export data directory contains data about the export table. So export table contains all the exported functions that have been exported by this PE file. Now PE files can be either EXEs or DLLs. So if it's a DLL, it contains a lot of functions that are exported to other PE files, right? So export table contains all of those functions. Then there's import table. Import table contains all the imports that are being done by this particular PE file. Resource table contains all the resources that are used by this PE file, that are icons, all the various windows that we have inside PE files. All that is contained inside the resource data directory. There are a bunch of different data directories. The security one contains the security certificate that was used to sign this particular PE file. Now, this can be used to identify whether a particular PE file was signed by a particular company or not. So this is basically used by the Windows loader when it tries to run any PE file. This is what causes the pop-up that you see. This particular software has not been signed by Microsoft. So this is what causes that particular pop-up to come up. The copyright one contains all the copyright information. Import address table contains all the information about various import addresses. Now, code injection. PE backdooring basically means injecting malicious code inside benign PE files to make it perform malicious tasks. There are various code injection techniques that are currently available and currently being used. The first one and the easiest one is custom section addition. Custom section addition basically means you add a custom section at the end of the PE file once all the original sections are completed, and then change the address of the entry point inside the optional header to point to that particular section. So instead of the execution occurring inside the normal text section, the execution would take place inside your custom section. Now, this, while it's really easy to implement this technique, it's really easy to detect it as well, because there are like custom sections are really easy to find. Like endpoint detection systems would could just search for the section names and find out, okay, which sections have inappropriate names, or which sections, or whether they have inappropriate permissions, because a section cannot just execute code because code exists inside that section and the address of the entry point has been changed to that section. We need to also make sure that the section has execute permissions as well, right? So it's the ratio of the stealth gained by this particular technique and the time required for a correct implementation of this technique is way too low, right? So it's basically very difficult to implement. PE code caving. So PE code caving is a technique wherein we try to find out the code caves that exist inside a PE file. Now, what are code caves? Code caves are basically a set of nulls and unused values that are present inside the PE file. PE file, while even small PE files have large amount of data that is contained in it, and not all of that particular space is being used, right? So they might have sets of nulls that are not being used by the Windows loader to do anything specifically. So those nulls could be used to store our malicious code. But we cannot just find these code caves and inject code into it. We need to make sure that the code caves exist inside a section that has execute permissions. So that is a task that is really difficult because it varies from binary to binary, right? Because a binary one may have code caves present inside the text section that can fit our malicious code. Binary 2 may not. So this technique is not really it does not work every time, right? Also, like I said, the disadvantages are finding code caves inside the PE files is really difficult, and finding a code cave that has execute permissions is even more difficult. That can fit your malicious code. So I had a question. Why not just edit the text section instead? Like just edit the text section, make it larger, fit your code inside it, and make it run, right? So what Perfidious is trying to do is Perfidious tries to fingerprint the entire PE file, break it down into individual blocks that can be increased or decreased in size, use the function to directly input malicious code inside the text section of a PE file. It extracts the text section, combines the code that is present inside the text section with the malicious code using jumps, and then uses the then assembles the PE file from ground up, right? This is a technique that is now advantages of this approach is it's really difficult to detect if done right, because there is no clear indication of a code injection occurring, right? You are not adding a new section. You are not adding code caves. You are not, you'll basically be recalculating all the checksums. So there'll be actually no way to detect whether PE injection has occurred or not, right? The problem with this approach is it's really difficult to implement. If you cannot really control all the fields inside every single structure inside a PE file, this cannot really be done, because you need to make sure that once the malicious code is injected within the text section, you need to recalculate all the different calls that are being made to addresses inside the benign text section, because the dot data section and each and every section beneath the text section will move downwards, because you have added it's like you are replacing a smaller block with a bigger block, right? So the calculations will vary. You'll need to make those calculations again, apart from changing all the data fields inside the optional section, the file header section, and increasing the size of the PE file as well, right? So this is really difficult to do unless you have complete control over your PE file. That is what Perfidious aims to do. Perfidious aims to make sure that you have complete control over your PE file. You can edit each and every section and structure that is present inside the PE file, right? So how would you detect such an injection that occurred inside your PE file, right? If an injected PE file using Perfidious was presented to you, how would you try to detect it? if your system has only allowed for whitelisted software, as in you have software that you know can run on your system and you verify the checksum values of that particular whitelisted software, you can detect injection, because the checksums will vary, because the checksums will have recalculated to accommodate the changes in the PE file. You can perform graph hash analysis. If any of you attended the talk that was given yesterday on graph hash analysis, you would know that graph hash analysis basically tries to create a hash value of the call graph of the entire structure. So what this does is this basically takes the .text section into account when it's creating the hash. It's not blindly creating the hash based on the values that are present inside the PE file, right? So this would easily catch the changes that are made in the .text section, because the call graph would vary because of the jumps that are inserted inside the PE file, right? So I'll give you the demo of the library itself. I tried to run the demo one of the code injection occurring, but it did not work. So I'll give you the demo of the library itself. So I'll first show you what this thing is doing. So this is basically an overview of how Perfidious will work. So you can just import a PE object that is pointing towards the .exe file or .dll file that you have on your file directory structure, and then you can basically say PE object, okay, I want to print the optional header of inside the PE file. Right. So I want to extract the optional header. It basically, like the first time Perfidious runs, like the first call to the class PE, what it does is it automatically parses the entire PE file and makes all the necessary class structures that are needed in order to perform any operations that you want. After that, you can just call the particular object that is present inside the PE file to print that. So when I say PE object.optional header, what it will do is it will print the optional header that is present inside that particular PE file. So this is basically the structure that it creates. So as you can see, it gives you all the DLL characteristics that are present inside the PE file. It's not just giving you the hexadecimal values and the byte values that are present inside it. It actually gives you the corresponding meaning to that particular structure. It gives you all the subsystem types and each and every field that is present inside optional header, along with all the various checksums that you might need for doing malware fingerprinting. So this is just one example of what Perfidious can do. My aim with this project is it should be able to edit each and every structure that is present inside the PE file, and it should be able to, it can be used to develop malware signatures that are not simply based on byte values, right? They are based on the actual values that are present inside the PE file. This basically rich header, the optional header, the hashes that are used inside that PE file. This gives you complete control over your PE file. So this can be used inside your endpoint detection systems to develop better malware detection rules. That is what I'm aiming to do. So that is basically the future of the project. Thank you for your time. And if you have any questions.
Warm round of applause, please, for Shreyans. Sorry for speaking too loudly. Okay, so we're going to have question time now, and as we did yesterday, we're going to have prizes for the best questions. Okay. Oh, and you have swag. Yeah. Awesome. All right. So first, I'm going to throw it open to the floor, and then I'll go to Slido questions. Anyone from in the audience who would like to ask a question, please? No, all shy. Yes, sir.
Why do you think that the DOS header in the PE header is not removed by the Microsoft?
It's not removed by Microsoft?
Yeah, it's not yet removed.
Backward compatibility. That's the only answer they have for everything that they do. Like,
but it's not the DOS is not being used anymore.
Yeah, exactly. Yeah. It's for backward compatibility. They are trying to ensure that their PE files basically run on each and every possible system that exists from. That is one of the reasons why they did not change the CMD, the horrendous CMD, to something better. They had to develop Windows Terminal from ground up for that particular reason, because they couldn't keep up with the backward compatibility and couldn't make CMD better anymore.
Yes, this gentleman here.
Okay, like Windows Vista onwards, you have applications, that could be run in compatibility modes, right? I mean, it could as back as Windows XP, like in Windows, even in Windows 10. When you enable an executable to run like that, does that in any way modify the headers? And if yes, you know what section is modified? I'm just trying to see that if that could be exploited in any way.
So my understanding of that is basically the headers will change depending on the like the exe. So I'm trying to understand your question. What modifies the header? Like what part are you trying to ask modifies the header
so,
exactly?
Like if you, so if an app that's been made to natively run on, let's say Windows 10 or Windows 7, right? And you try to make it backward compatible, okay, to run on say Windows 2000 or Windows, okay, sorry, let's not go to 2000, Windows XP or let's say Windows 8. So as soon as you apply that app compatibility shim, okay, as we call it, right? So it makes registry entries. So I'm not aware what part of header, I mean, what does it modify? And does that actually, I mean, in any way, I mean, I'm just trying to understand that is that a technique that could also be exploited? Could
That's
also
a
be
great
used?
question. My understanding of this is basically Windows Loader basically ignores the fields that are newer in the PE file structure and basically only uses the fields that it needs. Depending on the Microsoft version that, basically the Windows version that it's running on, it will basically use the fields that are relevant to that particular version. It will just ignore the fields, the other fields that are present. So if you look inside the PE structure, like in depth, you will see reserved fields that are present inside the structure. Now these reserved fields are not being used right now, but they are being present. They are present inside the PE structure to ensure that the future versions where these fields may be used, that will not break compatibility with the current versions. So that is my understanding of how this works.
All right, thanks.
There was one more question on this side, right behind you, the gentleman with the green shirt.
Hi, good morning. You were saying a while ago that you will also be rebuilding, calculating the addresses of the calls, for example, if you're going to inject some code in the PE file. But what if it has a relocation section? Would you be able to also recalculate and rebuild the reloc section?
Yeah, so that is where the
a follow-up question is, will this be compatible for both 64-bit and 32-bit Windows?
So about 32 and 64-bit, it can currently parse both types of files. So it's compatible with both those types of files, 64 and 32-bit EXEs and DLLs. About the relocations, so a lot of that data is stored inside the data directories. That is, like, I'm working on how to parse those things, but I'm pretty sure that once I'm able to parse data directories that are present, I'll be able to calculate all those relocations as well. So basically what I'm trying to do is I'm trying to get as close to Windows Loader emulation as possible. That is what I'm trying to do. So it will have all the functionality, like all the parsing and the implementation functionality that is present inside a Windows Loader. It will be able to do all those calculations that a Windows Loader does, but it can do it as a Python library. I hope that answers your question.
Any more from the audience? If not, then Shreyans will go to the question on Slido. We'll take the most upvoted one so far from Anthony. How will this tool behave when most endpoint systems have behavioral-based detection systems in place, such as Windows Defender Advanced?
Yeah, so it fails there because what it is trying to do is inside those behavioral-based detection systems, they are trying to do dynamic analysis. It will be caught based on what your shellcode does, right? So if your shellcode does something outwardly malicious, like uses PowerShell or opens outbound connections or something like that, it will be detected very easily, right? Is there a type?
So maybe we can answer one more question and then you can vote. You can choose your favorite question and we'll also give a prize to Anthony for the most upvoted question.
Okay.
We can answer all three. I think we have
Okay.
we have a
Is-
couple minutes left. Yeah.
In the current threat landscape, more common modes of attack like PowerShell are being more commonplace. Is there a good reason to fall back on PE executable based injection payloads again? So if you see the current scenarios, basically most endpoint detection systems can easily catch PowerShell based payloads, right? Because they have system in place to easily detect whether a particular PowerShell command is being run. So PowerShell based malware can run on systems that don't have those endpoint detection systems and have not disabled PowerShell, but otherwise it's not the future, according to me.
Okay. So Anthony, are you here? No? Oh, you asked 4 questions yesterday. You almost missed the upvoting prize yesterday 3 times. Oh, too bad. Okay, so Shreyans, which one's your favorite question?
The one the gentleman asked about the Windows.
Okay, you get a prize.
Yeah, like I can give it to everyone who asks questions. So
Okay, go ahead.
yeah.
All right, so I'll let you give them the prizes later, and then we'll have the next speaker come out on stage to get ready. Thank you.
you
Another
so much.
round of applause, please, for Shreyans.